What's up, mathlads? Episode 5 of our Algebra series has arrived. Today is a big leap, because we're going to be proving one of the most important theorems in group theory. We're going to prove non-singular matrices form a group. Okay, no. We're going to prove Lagrange's theorem. And Lagrange's theorem is probably the most important theorem in the first semester course in group theory. And if you don't understand it, you'll be labeled as a mathematical outcast, void of purpose, and undeserving of worth and validation. Everyone will look down on you for being the least prepared and dumbest person in class. Not really, but that feeling will haunt you for the rest of the semester. So before we jump into the statement of the theorem, we need to talk about cosets. There are left cosets and right cosets. Because guess what? Groups don't have to commute. Basically, cosets are a product, so to speak, between an element and a subgroup. By product, I mean the set that is a collection of products between the element and each element of the subgroup. So let's take integers and talk addition as a product for a second. Even integers are a subgroup. If we observe, say 3 plus 2z, we take 3 and add it to every even integer. What you may notice is that this actually produces all odd integers. If we look at, say, 1 plus 2z, it's actually the same set. We'll elaborate on this a little later, but hopefully what you'll notice is that 1 plus 2z is a coset containing all odd integers. Now consider 0 plus 2z, which contains all even integers. If we decide to go with either odd or even representatives, we may have the same set as a result anyways. So there are two cosets associated with even integers. Let's look at D6 and the subgroup of rotations without the flips. Details about this group are in episode 2. If we multiply the elements of D6 with every element of the subgroup, we actually only get two distinct sets. A brute force way to approach finding these lists might be using a Cauchy table and just excluding the elements from a column that aren't a part of your subgroup. Be careful here because commutativity isn't guaranteed, so you need to specify which cosets you're observing. In this case, it's the left cosets, which look like this. Now, I'm going to throw you a big tiffé. This is sort of a lazy way to write the following are equivalent, because who needs to write it out like that? People with nothing better to do with their time. If you write like this, I'm not shaming you, but I'm judging in a less than silent manner from afar. So, tiffé. G1h equals G2h, which means two different cosets are equivalent. H G1 inverse equals H G2 inverse, which means that the inverse right cosets are equivalent. G1h is a subset of G2h, which means containment is just as good as equality. G2 is contained in GH1, which means that if you have an element in the coset associated with that element is equivalent to the original coset. And G1 inverse times G2 is an H, which means if that product is an H, then that's also equivalent to saying that the two cosets generated by those two elements are equivalent. Now, if any one of these things is true, then it implies all the other properties. One other thing that is important to note is that cosets partition a group into an equal number of pieces. Okay, let's back up. What? So basically cosets evenly split up a group with no overlap. If I have two different cosets, they're either distinct sets with the same number of elements, or they're exactly the same set. And this is true for every group. They don't have to be integers or cyclic groups or symmetry groups or anything. Every group, all of them, can be split into even cosets. This fact is what leads to the intuition behind Lagrange's theorem. But maybe you don't trust me. After all, I'm just a guy that makes videos on the internet.
Or am I?
How could I possibly be any bit trustworthy when I haven't shown you any pieces of paper or research that says I have any clue what I'm talking about? The answer is I don't have to, and we'll prove these facts anyways. So we have to prove two things. Number one is proving any two cosets are either distinct, in other words, their intersection is the empty set, or that they're the same. So observe G1h and G2h, which are two cosets of h and g. Suppose to the contrary that their intersection is not empty. Then there exists an element A in both sets such that A equals G1H1, which is equal to G2H2, since it's an element of both sets. This implies that G1 is equal to G2H2H1 inverse, which is an element of G2H. So by our equivalent statements from before, G1H is G2H. So we've shown that if two cosets are not distinct, they're just the same. So, side note, the index of a group H in G, G:H in brackets, is the number of cosets associated with the subgroup. So, if there are two distinct cosets for a subgroup, then the index of the subgroup within the group is 2. Now let's move on to number 2, which is proving that each coset has the same number of elements. Another way to say this is to show that there exists a bijection between EH, which is just H, and GH for any non-identity G. Bijections are covered in episode 5 of the Foundation series, if you want a quick refresher. Let phi, or phi, doesn't really matter, from h to gh be defined by phi of h equals gh. Then we need to show that it's 1-to-1 and onto. We could show it's one-to-one by assuming that phi of h1 equals phi of h2, meaning that gh1 equals gh2. If we left multiply by g inverse on both sides, then h1 equals h2, which shows that it's one-to-one. To show that it's onto, consider gh to be some element of our codomain, gh. We can of course find an element, namely h, that gets mapped to gh, hence the cardinality of h is equal to the cardinality of gh. Now we're ready. The moment you've been waiting for. Lagrange's theorem. Lagrange's theorem says that the time derivative of the partial derivative of the difference between the kinetic and potential energy with respect to the time derivative of the position is equal to the partial derivative of the potential and kinetic difference with respect to the position, oftentimes used for classical mechanical systems.
No.
Ow.
Bad.
Oh.
This isn't physics.
Ow. I'm sorry.
This is pure math. Now do it again.
Ow. Yes, sir. Lagrange's theorem actually states that the order of a subgroup must divide the order of the group for any finite group G. Now, here's the proof. Any group can be partitioned into some number of distinct cosets, and each coset has cardinality equivalent to H. So the order of G is equal to the order of H times the number of distinct cosets. In other words, the order of G is equal to the order of H times the index of H and G. It's almost comically simple. Lagrange just waltzed in like, hey, I'm gonna prove something about every group ever that'll help yield insights about the structure that every group has to adhere to. So what else can we gather as a result? Well, if we have a cyclic subgroup generated by an element of G, then that subgroup will divide the order of the group. And moreover, if the order of the group is prime, then the group itself must be cyclic, since any non-identity element will form some subgroup that isn't just the identity. So it'll just create the entire group instead. All that said, be careful with this theorem. Note that if a number divides the order of a group, that doesn't mean that there has to be a subgroup with that order. It means you're not being a good enough mathematician. Try harder, then try harder, then try harder, then burn out and spend the year after you get your degree teaching as an adjunct only to realize that grading sucks because sometimes you just want to fail the student that writes exclusively in neon pink. Welcome to the education system. Anyways, I hope you liked this video. Please leave a thumbs up, subscribe, and leave your thoughts and questions in the comments down below. Thank you for your time, and keep learning.